Hello, everyone. My name is Paul Fanto, and during my time in the SSGF, I was completing a PhD in theoretical nuclear physics at Yale University with my advisor, Professor Yoram Al-Hasid. And today I will be discussing statistical properties of nuclei beyond the mean field approximation. The motivation for my work is the modeling of compound nucleus reactions. The compound nucleus is an equilibrated system in which the projectile fuses with the target nucleus, and this fused system statistically equilibrates, meaning that it forgets, in some sense, how it was formed. Theoretical models of compound nucleus reactions are needed to calculate reaction rates for many important scientific and technological applications. For example, compound nuclear reaction rates are necessary for studying rapid neutron capture process, or R process nucleosynthesis, which is responsible for producing the most neutron-rich nuclei. For instance, this figure shows the particular peaks in red of heavy nuclei that the R process is responsible for. Compound nucleus reactions are also important for nuclear data evaluation. The nuclear data evaluation is the process that provides databases of important nuclear reaction quantities, including reaction rates, that are used in research, defense, and technological applications. In the evaluation process, a large-scale reaction code is fitted to experimental data where this data is available, and then extrapolated to describe all the other nuclear reactions of interest. The wide impact of nuclear data is shown in this figure, which I took from Professor Lee Bernstein, who's at UC Berkeley and is the head of the Bay Area Nuclear Data Group. And he makes the point that nuclear data impacts not only nuclear science and nuclear astrophysics, but also the stockpile stewardship science program, where nuclear data is used to model nuclear weapons, non-proliferation, where nuclear data is used to design detectors sensitive to fissile material, nuclear energy, where nuclear data is important for validating novel reactor designs, and even metal isotopes, where nuclear data is used to study the production of important theranostic isotopes. To calculate reaction rates for compound nucleus reactions, nuclear physicists use the statistical model of compound nucleus reactions, also called the Hauser-Feshbach model. In this theory, the cross-sections depend only on the relative probabilities of competing reaction channels, a reaction channel being a particular way that a compound nucleus can form or decay. These channel probabilities, in turn, depend on average structural properties in the nucleus, called statistical properties of nuclei. In particular, these channel probabilities depend on the number of nuclear levels per unit energy, which is called the level density, and the average probability of decaying to a given level via a specific reaction channel, which is quantified by the strength function for the various reaction channels. In practice, then, these models of statistical properties in nuclei are used as input to a Hauser-Feshbach code, which in turn produces reaction rates that are entered into a nuclear database and applied in a variety of important research, science, and defense applications. The main question of my PhD research is how to improve these models of statistical properties. And the question that I'll focus on in this talk is how can we improve the level density models that are used in statistical reaction codes? First, I will highlight the limitations of the current level density models. Most reaction codes rely on phenomenological level densities, which are parameterized functions that are fitted to data where this data is available, and then extrapolated to describe other nuclei. The problem with these phenomenological models is that they become unreliable when extrapolated in this way. And this problem is compounded because level densities are challenging to measure, and so data are typically available only in restricted energy ranges. This figure here highlights this problem nicely. The purple dots show recent experimental data for the level density of germanium-76, while the blue triangles and the histogram show older experimental data. The lines show a set of phenomenological models, and you see that while these models agree well with the older data, they disagree with the more recent data, even at just slightly higher energies. These sorts of inaccuracies are important because nuclear reaction rates are very sensitive to level density variations. This figure, for example, shows how relatively modest differences in the value of a single parameter between two reaction codes, the differences in these parameters, this parameter is shown in blue, can lead to factors of 2 to 3 differences in the calculated cross sections. A useful goal then would be to replace these phenomenological level densities with microscopic level densities, which are calculated starting from an underlying effective interaction between the protons and neutrons. However, current microscopic approaches also have limitations. The mean field approximation is the main microscopic method that is used in practice for Hauser-Feshbach codes. In a mean field approximation, the full nuclear interaction is replaced with an effective, self-consistent one-body potential in which independent protons and neutrons move. However, these mean field approximations cannot or do not include important correlations that significantly affect the level densities. In particular, mean field methods do not describe the collective enhancement that is observed in heavy deformed nuclei. I show an example here for dysprosium-162. This collective enhancement is attributed to the presence of rotational band states, which are excitations that can be thought of intuitively as collective rotations of a deformed nucleus, and which are not described in a mean field approximation. In practice, empirical models of this collective enhancement are used to augment a mean field level densities, but these empirical models also become unreliable when extrapolated. In contrast, the configuration interaction or CI shell model introduces very little systematic error into level density calculations. In this method, the protons and neutrons fill sets of orbitals, which are depicted schematically here by the black lines. And then the nuclear interaction mixes up these configurations, hence the name configuration interaction. The conventional shell model methods essentially consist of diagonalizing a large matrix, and the dimension of this matrix becomes prohibitively large for heavy nuclei, restricting the use of this method. These limitations of the mean field approximation and the shell model motivate my use of the static path plus random phase approximation, or SPA+RPA. The basic idea of the SPA+RPA is to calculate level densities and other statistical properties of heavy nuclei starting from nuclear observables at finite temperature, all calculated in the framework of the configuration interaction shell model. Unlike the mean field approximation, which considers only a single effective non-interacting nuclear system, the SPA+RPA integrates over an ensemble of effective non-interacting systems. The integration variables that specify the different members of this ensemble are known as static auxiliary fields, and these fields define external potentials in which the independent protons and neutrons move at each integration point. Beyond this purely independent particle picture, the SPA+RPA also accounts for small amplitude and time-dependent quantal fluctuations within a method known as the random phase approximation. The SPA+RPA was developed in the 1990s and found to be very accurate in solvable models above a low breakdown temperature at which the method fails. The advantage of this method is that the calculation at each integration point can be done in reasonable computational time. The challenge is to evaluate the integral over all the static auxiliary fields. And we overcome this challenge using a Monte Carlo method, as I'll describe in more detail on the next slide. Although our work is the first to apply a Monte Carlo method to the SPA+RPA, such Monte Carlo methods are prevalent in nuclear physics. And in particular, a closely related method is the shell model Monte Carlo, or SMMC method, which includes even more correlations beyond the mean field and can calculate a large family of finite temperature observables exactly. As I'll show later in the talk, the SMMC provides a very useful benchmark of the SPA+RPA. Here, I will discuss the Monte Carlo method that we use to calculate finite temperature observables in practice in the SPA+RPA. In the SPA+RPA, an observable O can be expressed as this expectation value with respect to a weight function W, where sigma denote the static auxiliary fields. And expectation values of this form can be estimated by taking an average over independent sample configurations sigma k that are drawn according to the weight function W. In order to generate these samples, we execute a random walk in the space of static fields, and we guide this walk using the Metropolis-Hastings algorithm. In this algorithm, each step along the walk consists of two parts. In the first part, we propose an update from the current configuration that we're at, sigma, to a new configuration, sigma prime. And then in the second part, we accept this step with a probability that is given by the ratio of the weight function at the new point to the weight function at the old point. A key feature of this method is that while we will always take a step from a less probable configuration to a more probable one, we also have a non-zero probability of going from a more probable configuration to a less probable one. And this allows the method to explore the integration range of interest. We take samples along this walk that are separated by enough steps so that they are approximately statistically independent. And then the averages over these decorrelated samples estimate the true expectation values. And the standard deviations quantify statistical errors on these Monte Carlo estimates. The power of this method comes from the fact that its computational cost scales very gently with the number of integration variables. To study the accuracy of the SPA+RPA in heavy nuclei, we calculated the nuclear state densities of the samarium isotopes 148 to 155 samarium using this method. These isotopes describe the crossover from vibrational to rotational collectivity in heavy nuclei. The nuclear state density differs from the level density in that it counts all the 2J+1 degenerate states associated with a level of spin J individually, whereas the level density counts this group of degenerate states as one level. We calculate the state density rho from the thermal entropy S and the heat capacity C, where the temperature T is fixed so that this energy argument E is equal to the thermal energy. We show the results here for the even mass samarium isotopes. The SPA+RPA state densities shown by these orange circles are in excellent agreement with exact state densities that we calculate using the shell model Monte Carlo method or SMMC method, which I briefly discussed a few slides ago. We also find that the SPA+RPA is in reasonable agreement with experimental state densities from the counting of levels at low energies and from the spacing of neutron resonances shown by this red triangle. The green dashed dotted lines show mean field state densities calculated with the finite temperature Hartree-Fock-Bogolubov or HFB approximation. And as the neutron number increases, we see that the SPA+RPA state densities become increasingly enhanced over the mean field state densities. To look at this collective enhancement of the state density more closely, we define the collective enhancement factor, K, which is the ratio of the state density to the mean field state density. Again, we see that the SPA+RPA enhancements shown in orange are in nice agreement with the SMMC results and also in reasonable agreement with experimental data shown by this red triangle. For samarium 150 and heavier, a plateau of roughly a value of 10 appears in this collective enhancement and persists to higher and higher excitation energies, eventually damping to 1 at very high energies. This is what is called the collective enhancement. Its origin is the presence of rotational band states, which can be thought of as collective rotations of the entire nucleus and that are not described in the mean field HFB approximation. And the key takeaway here is that the SPA+RPA naturally describes this collective enhancement without the need to introduce an empirical collective enhancement factor. Finally, I show here the results for the state densities of the odd mass samarium isotopes. Again, we see that the SPA+RPA results shown in orange are in excellent agreement with the exact SMMC results shown in blue, and also in reasonable agreement with the experimental data. In summary, I have shown that the SPA+RPA can be applied to calculate state densities of heavy nuclei with a Monte Carlo method. The SPA+RPA state densities of samarium isotopes that we calculated are in excellent agreement with the exact SMMC state densities and in reasonably good agreement with experimental state densities. And finally, the SPA+RPA naturally reproduces the collective rotational enhancement of the state density in heavy deformed nuclei. In future work, we hope to extend the SPA+RPA calculations to actinide nuclei, such as uranium, and also to calculate gamma ray strength functions of heavy nuclei with the SPA+RPA. This is work in progress, and these strength functions are other important statistical properties of nuclei. Before finishing, I want to extend my sincere thanks to the SSGF and to everyone who makes this fellowship program possible. The fellowship introduced me to a wonderful community of scientists, from my classmates in the 2017 incoming year to the many other fellows and alumni that I met at the program reviews. The fellowship also gave me the opportunity to study nuclear reaction physics at Los Alamos National Laboratory during my practicum, and I would like to thank my supervisor, Dr. Toshihiko Kawano. And finally, the fellowship broadened my scientific horizons by allowing me to attend many conferences, and I highlight in particular the Stewardship Science Academic Program Symposium that I was able to attend last year. To look to the future, next month, I will be moving to the Washington, D.C. area and joining the Institute for Defense Analyses. The SSGF played a key role in this opportunity. I learned about the IDA through an SSGF alumnus whom I met at a program review, and through another scientist whom I met during my practicum. I very much look forward to remaining part of the SSGF alumni community in the years ahead. So thank you very much for your attention.